Lesson 2 in our unit on thermodynamics is about describing gases both macroscopically and microscopically. And this lesson might feel a little bit like chemistry because we're dealing with a lot of stuff that's normally seen in chemistry courses, but it's very important for understanding the first and the second laws of thermodynamics. Gases are, of course, considered fluids along with liquids, but they have a slightly different look and feel when it comes to thermodynamics. So, starting with the macroscopic description of gases, most of what you're going to see you probably should have seen before, because we're talking about the ideal gas law, which is PV equals nRT. And in this equation, P is, of course, pressure, V is volume, N is the number of moles, or the amount of gas, and T is the temperature. R is what's called the universal gas constant, and for our purposes, it has a value of 8.31 joules per mole Kelvin, and that's in SI units. Now, of course, R can have all kinds of different values. It may have values using ATM for pressure. It may have values instead of Kelvin using degrees Celsius. We want to stick with SI units all the time. As long as you do that, you can't go wrong. So 8.31 joules per mole Kelvin, and as long as you're using SI units for pressure, volume, moles, and temperature, you're going to be okay. So moving along, you've probably come to know that the most confusing aspect of using the ideal gas law is, of course, calculating the amount of substance. Getting your head wrapped around the number of moles of a gas is probably the most difficult concept to master in this part of the lesson. So basically, we need to remember that the number of moles of anything is equal to the mass divided by the molar mass. And of course, molar mass is, by definition, different for every single element and molecule that we get from the periodic table. Molar mass is also often called molecular weight. And so we're going to do a couple examples. But that information you pick right off of the periodic table. And it's usually something that's right on there, and you just find the molar mass of it or the atomic weight of it. And then we calculate the number of moles. So here's a quick little example. Determine the number of moles in a 12-gram sample of helium and the number of moles in an 88-gram sample of carbon dioxide. All right, so let's look at helium first. From the periodic table, we find that the molar mass of helium is about 4 grams per mole. And so now we can use our equation, N equals mass over molar mass, and we will divide the 12-gram sample by 4 grams per mole, and lo and behold, we find that, hey, a 12-gram sample of helium is 3 moles. Turning our attention to carbon dioxide. For here, the molar mass, we need to do something a little bit more. We need to take into consideration the molar mass of the 1 carbon atom and the 2 oxygen atoms. So this is what we've done here. 12 plus 2 times 16, we get a molar mass for carbon dioxide of 44 grams per mole. And if we put this into our formula, we end up with 88 grams divided by 44 grams per mole, which very nicely works out to 2 moles of carbon dioxide. Moving along, we know that we can also express the number of atoms or molecules that exist in any mole, in 1 mole of any substance. And so, of course, this number is known as Avogadro's number, and it has a value of 6.02 times 10 to the 23rd. And of course, the units on that will be moles to the -1, or inverse moles. And so from here, we can then say, oh, well, we can use Avogadro's number and the number of moles to determine the number of particles. So let's do that. Determine the number of atoms of helium and the number of molecules of CO2 in the samples given in example 1. So here we're going to use the number of moles is equal to the number of particles divided by Avogadro's number. And for helium, we had 3 moles. And of course, Avogadro's number is 6.02 times 10 to the 23rd. So hey, the number of atoms of helium was 1.81 times 10 to the 24th. And very similarly for carbon dioxide, we had 2 moles of carbon dioxide, and we're going to multiply by Avogadro's number, and we get 1.204 times 10 to the 24th molecules of carbon dioxide. So why is all this important? Well, we're dealing with gases. And so because we're dealing with gases, we need to be careful how we count those atoms or molecules, as you've just seen. If the gas is monatomic, then each little bit of the gas is just one atom. If the gas is diatomic, then each little bit of gas is two atoms. If the gas happens to be a molecule like carbon dioxide or something else, then each little piece of the gas is made up of, in the case of CO2, one carbon and two oxygen atoms. And this will really create quite a difference in how we handle these problems, because the number of moles that we're going to get is going to be completely different. Sometimes, though, rather than working with moles, we could work with the actual number of atoms or molecules. And so then our ideal gas law looks a little bit different. It says PV equals N kBT. And Kb is the Boltzmann constant. And it has, again, an SI unit value of 1.38 times 10 to the minus 23rd joules per Kelvin. And oftentimes this will be a handy little formula to use. How many grams of oxygen are there in a 50-liter tank at 21 degrees Celsius when the oxygen pressure is at 15.7 atm? So this is a PV equals nRT problem. And what we need to do is first convert, because ATM is not SI units. Pascals are, of course, SI units. 15.7 ATMs, if you do the conversion, turns into 1.59 times 10 to the 6 pascals. Of course, liters is also not SI. We need to convert into meters cubed. And we get 50 liters is 0.05 meters cubed. Of course, R is the gas constant, and because we're using SI units, we use 8.31. The temperature has to be in Kelvin, so we'll convert our 21 degrees to 294 Kelvin, and we'll use our equation PV equals nRT. So we'll rearrange it first, and then we can sub in our values. And lo and behold, we get about 32.5 moles of oxygen. Now, this isn't the answer to the question, because we actually want to know how many grams of oxygen there are. And so now we take the molar mass of oxygen gas. And oxygen gas is, of course, a diatomic molecule. So our molar mass, we need to take 16 grams per mole, but we need to multiply it by 2, because this is the gas. The gas is O2. And we get 32 grams per mole. And so this is where we're saying you have to kind of be careful when you're doing these types of calculations, that you look at what the gas actually is. Is it monatomic? Is it diatomic? Or is it some molecule? And what we find here is that our molar mass is actually double what it would be if we didn't count oxygen as a diatomic molecule. Here now we can convert molar mass and the number of moles that we have into the mass of oxygen. And when we do that, we get 1.04 times 10 to the 3 grams. And so we can say, hey, there's about 1.04 kilograms of oxygen in the tank. And that's a pretty standard PV equals nRT problem. They're very similar to this. And we're going to move along. It should be mentioned, though, that for an isolated sample of gas, PV over T is equal to a constant. And sometimes this is very, very helpful, because it can help us to set up some proportions, right, to determine changes when we either alter pressure or volume or temperature and we're holding the other things constant. And so this will be very, very useful sometimes to do quick little calculations. If we flip now to the microscopic description of gases, the first question is, okay, well, why do we need both? And so the reason for that is a little bit historical. The ideal gas law provided great answers to macroscopic questions, but it was what we called empirically based, which meant that it was based on experiments and observations that we made, and we really didn't have any kind of theory behind why gases behave the way they do. So what happened was that they developed the kinetic theory of gases to really give the theoretical basis for why we observed what we did. And the kinetic theory involves 5 assumptions, and here they are. We assume that the gas consists of a number, and that number would be a large number of identical particles. So that's the first assumption. The second assumption is that the number of particles is very large, but the density is low enough that there's a large separation between the particles. The third assumption is that the particles interact only through elastic collisions with other particles. And the fourth assumption, the particles make elastic collisions with the walls of the container. And finally, we get to the last assumption, is that the particles have random directions and speeds, but they obey Newton's laws. So here's a whole bunch of assumptions that we're making, and they're going to allow us to do different things. What they're going to allow us to do is the following. Assumption 1 says, hey, all the gas particles in a given sample have the same mass because they're all identical. This mass is denoted by mu, and it helps us with the conservation of momentum and kinetic energy that's noted in assumption 3. Okay? Assumption 2 and 5 allow us to treat the gas using statistical means. And what that means is we can talk, instead of having to talk about the individual velocity of every single gas particle, we can talk about the average velocity of all the gas particles, and we're going to get the same results. We can look at the gas kind of in a collective way. Assumption number 4 allows us to describe the interaction of the gas with the outside world through the impulse it gives to the walls of the container. Okay? So this is what it's going to allow us to do. And really what we could launch into now is a full-blown derivation of the result that I'm going to present. However, in the interest of time, we're not going to launch into that derivation because it's pretty involved. If you would like to see it, check out any first-year physics or chemistry textbook. Even check out one of the AP study guides. They usually have it in there. We're just going to state the result. And what the result tells us is that the average kinetic energy of a particle within the gas is equal to 3 over 2 kB T. Kb being the Boltzmann constant and T being the temperature. And so what does the derivation and this result tell us? Well, for an ideal gas, number 1, and perhaps most important, temperature is actually a measure of the average kinetic energy of individual gas particles. So when the temperature goes really, really high, we can say that, hey, that means that those little gas particles are moving really fast. When the temperature's low, those gas particles are not moving fast, they're moving much slower. The second result that really is a product of the derivation, and you don't have the pleasure of seeing that, but that's that pressure is caused by the collection of gas particles rebounding from the walls of the container. That's really what pressure is. It's gas particles that are bouncing off the wall and creating pressure. And these two bits of evidence, these two things that came out of this derivation really provided the first direct confirmation that matter was made of atoms. And that was a big deal. That was a big deal when this was derived. So in a monatomic gas, so think about a monatomic gas that's like helium or something like that, that doesn't have, it's not like oxygen where there's two molecules that are kind of bound together by bonds. A monatomic gas is just a whole bunch of individual atoms floating around. So in a monatomic gas, we can do something special, and this is only for a monatomic gas. Really, the total kinetic energy is directly related to the total internal energy of the gas. So for n particles, the total energy given by U is equal to n times the average kinetic energy of one particle, which is equal to 3 over 2 n kBt, or 3/2 nRT. So that would be the total energy for a monatomic particle, the total internal energy. And we can use this information to define a special type of average velocity. It's called the root mean squared velocity. And really what it tells us is the average or the mean velocity that the particles are traveling at. Again, it's statistical, so it won't tell us the velocity of each individual particle. It tells us this is the average velocity of the particles. And of course, this is the root of 3 kBt over mu, which is of course the mass of one particle. So let's take a look at a couple examples. A tank used for filling helium balloons has a volume of 0.3 meters cubed and contains 2 moles of helium gas at 20 degrees Celsius. Assuming that helium behaves like an ideal gas, what's the total kinetic energy of the molecules in the gas? So we're looking for total kinetic energy, and remember, helium's monatomic, so the total kinetic energy is equal to the total energy. So here's our givens, and we're trying to find K average. And of course, we can use 3/2 nRT because this is the total internal energy. And we'll make a little substitution, and of course what we find is 7.30 times 10 to the 3rd joules. Don't mix this up, just incidentally, don't mix this up with the kinetic energy of just one molecule, which was given earlier. We should keep these separate. This is the total kinetic energy of all of the molecules, not just of one of the molecules. The next example, hey, a sample of 10 moles of an ideal gas is originally at a pressure of 300 kilopascals. It undergoes an isothermal compression, which means a compression that happens at a constant temperature. And it goes from an original volume of 1.2 meters cubed to a final volume of 0.4 meters cubed. Find the final pressure of the gas. So here's what we're given, and here's what we need to find out. We need to find out P2. And remember we said that, hey, sometimes we can set up proportions to make things easier on us, and that's exactly what we're going to do. Because the temperature is constant, P1 times V1 is a constant, and that happens to be the same thing as P2 times V2. So here's our proportion. We can sub in our numbers, and we can solve for P2, and we find that it's about 900 kilopascals. That, by the way, is a very good example of what you could see in the multiple choice section of the AP exam, something very similar to that. This is another pretty typical sample AP exam question. A 1 mole sample of helium, a monatomic ideal gas, has a temperature of 40 Kelvin. Determine the RMS speed of the atoms in the gas. Well, here we know that we've got 1 mole, the temperature is 40 Kelvin, and we know that the root mean squared velocity is 3 RT over the molar mass. So we have to say, okay, well, what's the molar mass of helium? And it happens to be 4 grams per mole. But remember, if we're going to use 8.31 for our universal gas constant, we need to turn that molar mass of 4 grams per mole into a kilogram per mole. And that's exactly what we did here by multiplying by 10 to the minus 3. When we've done this, we can, of course, solve, and we get 500 meters per second, which is the root mean squared velocity.